In this video, I'll cover section 1.6 and section 1.7. They're just more techniques used to find the integrals and definite integrals when they have exponential logarithmic functions, and for section 1.7 when they have a formula that gives us an inverse trig function. So let's start with the main idea here, which is integrating exponential functions. When you have an exponential function, you're either going to use this formula or this one. So the first one is when we have a special base, which is my e, and the second formula is for any base a. I'm sure you've seen these before, and we did an example about it last time where we had an exponential function. So technically, these are just more applications, more examples on finding antiderivatives or definite integrals. So let's start with examples so we'll be more comfortable solving these questions. So for the first example here, I want to find the antiderivative for these following functions. So when I say I want to find the antiderivative, it's just evaluating the indefinite integral for that function. So here, I don't have this formula directly. So I want to build something or do something to solve a problem to get something that looks like this in the end, where I can just integrate it easily. If you remember from the last video, we talked about substitution. So here, if you look at the exponent of your e here, you have x squared. And if you look at the integrand in general, you see that you have an x here and a dx. So let's see what happens if I take u to be my whole exponent. If we're using substitution, you just find your u, then you integrate, and if you see, I have an x dx which is already in my integrand, which means my substitution is correct. The only extra thing is the -2, which I can easily just divide with. So now putting everything back, I'll have my x dx is just du over -2, and then I have e to the u. Using the properties of integrals, I can take the constant out. So now if you see, I got the desired formula where we only have e to the u. So using that formula, this is just e to the u. Since this is indefinite, I need to add c. And now once we're done, I need to substitute everything back again. And that would be the answer. Let's try the second example. Similarly, I want to evaluate the antiderivative. I'll look here. Also here, I don't have a direct e to the x that I can integrate easily, so I need to think about different methods. So far, we only learned the substitution, so it makes sense to substitute something. But what do I substitute here? So we said when we're doing substitution, if you have like a general function, an outer function, my f, I substitute everything that's inside of it. So here, if you take your u to be e to the x minus 2, let's try and find the integral, the derivative. So the derivative is just du, and then the derivative of this is just e to the x dx, which is perfect because I already have this in my integrand, which means my substitution is correct. So now, plugging everything back in, e to the x dx, this is just my du, and then I have a u here instead of e to the x minus 2, and it's cubed. If you integrate it easily by the antiderivative. Sorry, this is just u to the 4 over 4 plus c. But if we're doing substitution, you need to substitute the thing back again, and you get this. And the last example that we have, I want to find the antiderivative of this. So now I have the integral of negative x e to the x plus 1 dx, and we want to find the antiderivative. Now here, if we try different substitutions, like if I take my u to be what's inside of the main function here, if you find the derivative, you're going to get e to the x dx. But if you look at the integrand, I don't have it. I have e to the negative x. So this substitution is not going to work. I need to think about something else that might help me. So now here, since I don't have any powers, my power is 1, I can easily just distribute this to the whole parentheses. So once you distribute, you're going to get this. And now using the properties of exponents, if I have the same base, I can just add the power. So I'm going to get e to the 0, which is 1, plus e to the negative x dx. Using properties of integrals, I can distribute the sum here. Now this is easy. This is just x, right? But how about integrating e to the negative x dx? Since I have a function other than x in the exponent, I need to think about something that I want to substitute. Usually we just substitute the whole exponent. So you take your u to be your negative x, you differentiate, and you get this. Then I can just easily divide by a negative, since I don't have a negative here. So minus du is just my dx. So if you plug everything back in, this is just e to the u times minus du. So this is just minus the integral of e to the u du. Using the antiderivative of it, this is just negative e to the u. But if you integrate, you need to plug in x back in, and just take this answer, and this is just minus e to the negative x plus c. So it's just regular substitution with the rule of exponentials. Okay, let's write more examples. If I have this, and I want to evaluate these integrals, always look at your integrand. If you're able to substitute something and the derivative of that thing is already in your integrand, this means that your substitution is correct. If not, you either want to find a different substitution, or in the future, once we learn more methods, you want to find a different method that might work in your example. So let's look at the first part. Usually when you have an exponential, you take the exponent to be your substitution u. So here, if you take u to be the whole exponent, then you find the derivative. Now let's look. Do we have this in my integrand? If you look directly, you can't find it. But if I take negative 2 as a common factor, you're going to get 2x cubed plus x dx. Now this parentheses here is in my integrand. So my substitution is correct. The only thing extra here is the negative 2, which I can easily just divide to both sides. So du over negative 2 is just a part of my integrand. Plugging everything back in, this is e to the u multiplied by du over negative 2. using the formula of antiderivative here, I just get this, and remember to plug in your original substitution back in once you're done. For the second example, you look at the integrand. We said that we usually substitute the exponent, so let's try if that would work here. The derivative is just -2 dx, and if I have a number, I can just divide by that number. So the only thing that I want from the integrand, is dx, and I already have dx, which is perfect. But look, this is a definite integral. If I have a definite integral, I have bounds, so I need to find my new bounds. So here, when x is equal to 0, and when x is equal to 3, let's find the new bounds. Here, u would be just 1, and u would be -5, because you're plugging in your value here. So you're going to get this integral now from 1 to -5 e to the u times du over -2. But here, my upper bound is lower than my lower bound, so I can use the properties where I take the negative and I just flip the bounds. Negative with a negative cancels out, and the integral of e to the u is just e to the u, and I substitute the bounds. So that's e minus, so upper minus lower, e to the -5. So this is just substitution like we did in the previous video. Let's try this last example. I want to find the integral of e to the 1 over x squared over x cubed dx from 1 to 2. Let's try the exponent here. If you take u to be 1 over x squared, but you can easily write this as x to the -2, and you can find the derivative easily. So now, I need to subtract 1. So I get -3. So if you write it in a different way, this is just -2 over x cubed dx, which is perfect because I have x cubed in the denominator here, and I already have it here in the integrand, so the substitution is correct. But since I have an extra number, I can just divide both sides by that number, and we get this. If you have bounds, you need to substitute the new bounds and find the bounds for u. Once you substitute, this is just 1 and 1/4. So I'm going to get the integral from 1 to 1/4 e to the u times du over -2. The upper is less than the lower bound, so you can flip it, and I have a negative here, so this is going to be positive 1/2 from 1/4 to 1 e to the u du. Repeating the same process over again. This is 1/2 times e to the u from 1/4 to 1. So this is e minus e to the 4th. Like I said, you don't need to simplify anymore. This should be enough if it was on the exam. Now let me comment again. Although we want to find the new bounds and substitute the new bounds, you can always find your integral that you got from substitution as an indefinite integral once you evaluate it normally, Now, instead of adding a c here, what I do is I substitute the value back in, which is 1 over x squared, and I use my original bounds, which is 1 and 2 for the values of x. So if you now do upper minus lower, if you take negative as a common factor, you're going to get 1/2 e minus e to the 1/4. And if you notice here, I got the same answer. So it kind of depends on the question. Sometimes it's easier to find the new bounds and just substitute these back in without putting in the original value of x. And other times it's easier to just like leave these bounds as it is, evaluate the indefinite integral, plug in the value of x back, and just use the original bounds that you got. With practice, you're going to notice when substituting the bounds are easier and when leaving them as it is and plugging the values like back in terms of like x, for example, here would be easier. But if you like don't stress too much about it, you can always substitute the bounds and evaluating them, even if it's more difficult. If it's just easier for you, just do that, no problems. Okay, and now let's move on to logarithmic functions. So here we have three main formulas that are helpful. If I'm integrating x to the -1, so this is equivalent to integrating 1 over x dx. So when you have that, it's just ln of x with absolute value. If I'm integrating ln of x, this is just x ln of x minus x. When we go into chapter 3, we'll be able to integrate this and prove it, and we'll see why this integral is equal to this. And finally, if I have a log with a certain base a, I can easily find the integral using this formula. Okay, so let's do these examples together. If I want to find the antiderivative again, this is just the indefinite integral. So here, I can easily just use a u sub by taking u to be x minus 2. My du is just dx, which I have in my integrand. Then I'm going to have the integral of 1 over u du. Using the first formula, this is just ln of absolute value of u plus c. But since we're doing substitution, I need to put the original value back, and that would be the final answer. For part B, I want to evaluate the integral of log base 3 of x dx. Using the third formula, this is just x over ln of your a, but my a here is just 3, multiplied by ln of x minus 1 plus c. And the final example is the integral of this So now let's look here. I want to find a suitable substitution. So always think, can I substitute something where if I derive it, the derivative is going to be in my integrand? So let's try the numerator first. If you take u to be that, let's try and find the derivative. If you look at the derivative, it's nowhere in my integrand. So I don't think that's going to work. How about if I substitute my denominator? Once you find the derivative, you're going to get 4x cubed minus 2x dx. If you look at the integrand, technically this is nowhere in my integrand. But using the technique of taking a common factor as let's take like a 2. Let's see if that helps. So once you do that, this is just my numerator, which means my substitution is correct. So I'm going to get du over 2 is just this, which is in my integrand, which is perfect. So this is just the integral of du over 2 over u, because this part here is just du over 2, and then the denominator is just u. So this is 1/2 the integral of 1 over u du. Using the first formula, this is just ln of u plus c. And you don't forget to plug in the original value of the substitution back in. And that would be it. So it's all about practice. With practice, you'll notice these substitutions very easily. Now let's try to evaluate this definite integral. Here again, we either want to substitute the numerator or the denominator. So if you take the numerator, for example, you're going to get negative sine of x. Although I have a sine of x here, but I have a 2 added to that sine. So this is not going to work. So let's try to substitute the denominator. Let's find the derivative. This is just cosine of x dx, which is perfect because this is my numerator, which means my substitution is correct. Since I have bounds, let's find the bounds of u. So when x is 0, once you plug in 0 here, you're going to get 0 plus 2, so that's 2. Then, this is pi. Then once you plug in pi here, actually this should be pi over 2. Once you plug in pi over 2 here, you're going to get 1 plus 2, and that's 3. So now I have the integral from 2 to 3 du over u. So this is going to be equal to ln of u with absolute value from 2 to 3 using the first formula, and then upper bound minus lower bound. This is ln of 3 minus ln of 2. Using properties of ln, this is just ln of 3 over 2. So that's mainly it for logarithmic functions. They're just formulas that you have to memorize and then use to solve different problems. So these are some suggested problems from section 1.6. You can do them if you want to practice more, because they're going to be very helpful when you practice. And now section 1.7 is just integrals when we have inverse trig functions. So these are my main formulas that we're going to use. If you have anything of this form, this is just arc sine, which is my sine inverse of u over a. If you have something of this form, this is 1 over a arc tan u over a. Anything of this form is just 1 over a arc tan u over a. So these are just formulas that you should be familiar with. They're very easy to just apply. So let's see the first example. I have a definite integral from, this should be the square root of 2, from 0 to the square root of 2, and we want to find the integral of 1 over the square root of 4 minus x squared. If you look at the first formula, this kind of looks like it, right? So we're going to use the first formula, but my a, so here, this 4 is my a squared. Then the a is just going to be 2. Okay, so now if you apply it, this is just sine inverse of x over 2 from 0 to the square root of 2. So this is just the sine inverse of radical 2 over 2 minus sine inverse of 0. Using the unit circle, this is just pi over 4 minus 0, so it's just pi over 4. Let's see the next example. So here, although this kind of looked like the first formula, but not quite, because here I have an extra number with my x squared. So a, I know for sure it's just going to be 4, right? But since I have an extra 25, I need to do some u sub. So if you take your u to be 5x, then just deriving, you're going to get this. So why did I choose 5x? Since I want to use the first formula, I want to have something squared subtracted from my number. So if you substitute 25x squared instead of, like if you take u to be 25x squared, you're not going to have a square here. So to fix this problem, you just take the square root of this. So that's just 5x. So let's see what happens when you plug the substitution back in. Here I have du over 5 is my dx. So I'm going to have du over 5, the square root of 16 minus, so I can rewrite this as, let's rewrite it here. This is just 16 minus 5x squared. But since 5x is just u, I'm going to get u squared here. So this is 1/5 du over this. Using the first formula, this is just 1/5 sine inverse of u over my a. But we said a is 4, so this is just 4 plus c. Now, since we're doing a u sub, I need to substitute the value of x back in. And that's it. And my final example here, if you look at this integral, it kind of looks like the second formula here. A is going to be a squared is 16, then a is 4, and then if you look at the formula, I have an u squared here. So I need something squared without a number. So repeating the same trick that we did in this part, how about we rewrite it first? If I rewrite the denominator to be 3x squared, it's kind of obvious that my u should be just 3x. So if I take du is equal to 3 dx, then du over 3 is just my dx. Plugging everything back in, plus now this is u squared. I can take the number out. And now if you look, I got the main form of this second formula. So if you look here, this is just 1 over a arctan u. So this is times 1/4 arctan or tan inverse of u over a plus c. We are doing substitution, so don't forget to plug in the value of u back in. Plus c. So these are just formulas that you should be familiar with. They're not very common to come like in normal questions, but it's good to know because sometimes they're pretty useful. Also, these are some suggested problems from section 1.7 if you want to practice anymore. If you have any questions, please let me know. And don't forget that the first homework is going to be due this Sunday. Good luck with everything, and please email if you need office hours or if you want help with anything.